Uh, back in March, or even before March, when everything with COVID-19 came out, you heard a lot of people talking about, well, we need to flatten the curve. We need to flatten the curve. Well, in this chapter, we're going to learn what they mean by this curve that they're talking about. What is this quote-unquote curve that they kept referring to? Well, what we're going to look at is what's referred to as a normal distribution. And statistically, what they mean by a normal distribution is it's going to be something that can be described by a symmetric. We've talked about symmetric curves where we said one side's going to look essentially the same as the other. Single peaked, which means it only has one highest value. And since it's symmetric, that highest value is really going to be in the middle of our curve. Bell-shaped density curve. And you'll see when you look at the shape of the curve, it kind of looks like a bell. So a normal distribution is going to have a bell-shaped curve, but it's going to have a single peak, and it's going to be symmetric. A couple small notation things. Whenever they refer to the mean of a normal distribution, they're going to use the Greek letter mu. So if you ever see that, they're talking about the mean for that distribution. And then the standard deviation is represented by sigma. And again, if you ever see that, that means we're talking about standard deviation. So not huge things that you have to memorize or anything, just in case you happen to see those symbols, you know what they're talking about. Then if you go a step further, sometimes we look at what's called the standard normal curve. And the standard normal curve basically says, okay, I'm going to set the mean at 0, and I'm going to set a standard deviation of 1. We won't do much with a standard normal curve, but I put that on there to kind of give you an idea of how this curve would look like, or what this curve would look like. So first of all, some notation for the normal curve. Again, when we look at the mean and we look at standard deviation, we're going to refer to those with those symbols of mu and sigma. But the notation you usually see is you'll see a capital N to tell us we're going to deal with a normal curve. The first value, it's going to look like an ordered pair, but the first value will be our mean, and the second value will be the standard deviation. So if I'm talking about a standard normal curve, it would look like this, where they give you a capital N, they'd say 0, because that's the mean, and they'd say 1, because that's the standard deviation. So if I were labeling this curve here, and it was a standard normal curve, first of all, notice this is what I was talking about, that bell-shaped curve. So we have this highest point here. It's symmetric on both sides. Well, if it's really symmetric, we talked about when I look at our data, that symmetric data, we want to use the mean as our center point. So since the mean for this in a standard normal curve is 0, here in the middle, I would label that with 0. And whenever we label our normal curves, that's always where we'll start. We'll start in the middle, and we'll start with the mean. Then you'll notice there are 3 marks above that mean and 3 marks below that mean. Well, each mark is worth 1 standard deviation. So if my standard deviation is 1 in this case, that means this would be 1, this would be 2, this would be 3. You go in the opposite direction, it would be negatives then. So that would be an example of a standard normal curve. Well, big deal. Why is that important? Well, the reason it's important is when we look at this standard curve, each section is actually going to represent a certain amount of our data. So if I'm really looking at a normal situation, I'm going to use what's referred to as the 68, 95, 99.7 rule. And that sounds pretty fancy, but what that means is, first of all, the first part, the 68 part, tells me that about 68% of the values that I'm looking at will fall within one standard deviation of the mean. So if my mean is here in the middle, what that means is if I go one standard deviation to the left and one standard deviation to the right of that mean, 68% of my values will be in that range. Then as I start creeping out, that's the second part of my rule, the 95. Well, the 95 then means about 95% of my values, they're going to fall within two standard deviations of the mean. So now when I get out here, that's now going to be 95% of my values. And then the last part gets us to that third standard deviation, the 99.7. Means 99.7% of my data, so almost every single bit of my data gets me out to this third standard deviation. So the 68, 95, 99.7 rule is going to be true anytime I'm looking at a normal curve. So when they talk about flattening the curve, they weren't talking about changing these values, but what they wanted to make sure of was if 68% of our values are going to be in that highest peak, they didn't want that peak to get really high. Because if 68% of all the values or all the cases of COVID happened and it became really, really high, well, that was going to make it difficult on the hospitals. It was going to make it difficult for them to treat people. Versus they talked about flattening that curve. Well, it still would have a highest mark here. They just didn't want it to get to the higher level. So they wanted, if you're going to have 68% of your values, they wanted that to be a lower number versus it really peaking and getting to a higher number. So that's what they were referring to when they talk about flattening the curve. Now, this rule that we came up with actually helps us a little bit with what I call benchmark percentiles. So on that curve that I gave you there down at the bottom, hopefully you mark these parts to that on there. But we're also going to mark what I refer to as some benchmark percentiles. And here's what I mean by that. We talked about percentiles being the percent of values below a certain mark. So if I think about the mean being exactly in the middle, well, the mean is actually then at the 50th percentile. So that would be one of our quote-unquote benchmark percentiles. Well, then I know if I go one standard deviation each direction, that's a total of 68%. But I also know that my curve is symmetric. So in other words, it's exactly the same on each side. So if I took that 68 and I cut it in half, because that's how much I'd have on this side, that's how much I'd have on that side. Well, if I cut 68 in half, that's really 34. So if I increase this 34, that means this is the 84th percentile, 1 mark away. If I subtracted 34, this would be the 16th percentile on the lower end, 1 mark away. If I take the 95%, I cut it in half, well, that's 47.5 on each side. So that means this is the 97.5 percentile. And this would be 2.5 percentile. So again, remember what that means. That means only 2.5% of my values would be lower than that mark. Or over here, 84% of my values would be less than the 84th percentile. And then I can do that again with this last one, the 99.7. And when I cut that in half, what I find out is down here is 99.85 percentile. And this is just 0.15. Or in other words, only 0.15% are less than that bottom value. So no matter what situation we're looking at, if it's a normal curve, these percentiles will always be in those places, no matter what. So that's why those are important ones to have down. You don't have to memorize them, but to have them down to where we can transfer them over. So all this is a little bit confusing, I know, until you put it to a situation. So if you look on the back of that first page, let's see how this might tie to a certain situation. Well, this example talks about looking at the shelf life of a certain dairy product, and they find that that shelf life is normally distributed with a mean of 12 days and a standard deviation of 3 days. Or some way that, or one way you may see it written is you'd see a capital N, and then you'd see 12, comma, 3. Meaning 12 was the mean, 3 was the standard deviation. All right, well, before we try to start answering some questions related to that, I'm going to try to label my curve. A lot of times I'll ask you to sketch a normal curve and then label it. So I'm going to label my normal curve based on this data here, where they said the mean is 12. So that tells me I'm going to go to the middle here, and that's going to be 12. And then the standard deviation is 3, which really just tells me you're going to go by 3s as you go along. So if this is 12, this would be 15, 18, 21 on that side. And then I go by 3 still, 9, 6, and 3. So if I ask you to sketch and label normal curve, I'd be done now. That would be what I'd be looking for. I like to throw in this little extra though. I like to throw in those benchmark percentiles that we just came up with. So those benchmark percentiles that we labeled here are still true on this normal curve. So above that, I like to just write those percentiles in. You don't have to, but you'll see why I'm doing that here in a second. So again, you don't have to put those on there, but sometimes those are helpful to put on there. All right, so here are maybe some questions that you'd be asked related to that. The first one wants to know about what percent of the products last between 9 and 15 days. So the numbers that I wrote in black, remember, represent the days. So I'm looking at, well, what percent of those products last between the 9-day mark and the 15-day mark? Well, here's why those percentile markings are important, because both of these are on those benchmarks. So I know the 9 days is at the 16th percentile. I know the 15 is at the 84th percentile. So in between those two should be the difference between 84 and 16. So if I subtract 84 and 16, that would tell me what percent I have. Now, in this case, I already know it should be what percentage, since it's in that middle section. What do we say the middle section should have? 68%, right? So we can go ahead and do the subtraction, but in the back of our minds, we already know this really should be 68 because that was that middle section. But answering the question, 68% of our values would be between 9 and 15. All right, what if I'm asked between 12 and 15? Well, again, I go to those two values, 12 and 15. I look at their benchmark percentiles, well, that's 84 and 50, and I just subtract those two. So when I subtract those two, I find out that's 34%. All right, the next one wants to know about what percent lasts 6 days or less. So I go to the 6-day mark. I want to know 6 days or less, which really means they're asking what's the percentile. Well, the percentile at 6 days is 2.5. So we'd say it's 2.5%. Last one wants to know what percent of the products last 15 or more days. So this is slightly different. But I still want to go to that 15-day mark. I notice that's the 84th percentile. So that means 84% of the values are less than 15. How am I going to figure out what percentage are more than 15? We know the percentage is less.
You do 99.85 minus 84.
Almost. We're going to go ahead, and even though this was the last one we labeled, we're going to go ahead and think about all the values. So we'll go ahead and start with 100.
Okay.
But you have the right idea as far as the subtraction. So 100 is going to be all our values. The 15-day mark was at the 84th percentile. So 16% roughly of the values would be more than that 15 days. And so really there's only about 3 kinds of problems you could have. You could have the ones where you want to find in between two values, the percentage that are less than a certain value, the percentage that are more than a certain value. Here's kind of the kicker though. All these have been nice and neat values. They've landed right on one of our benchmarks. Well, what happens if it doesn't land on the benchmark? For instance, this question wants to know what percentage of the values last 16 days or less. And I go up here, and I notice 16 is not one of the numbers I wrote down. Well, when that happens, I've got to have another strategy. And this is where that z-score comes in. So if I find out that it's not on one of my benchmarks, I'm going to take that value and I'm going to find the z-score for that value. So to find the z-score, we know our value was 16. Originally, we already knew the mean was 12 and the standard deviation was 3. So nothing new as far as our steps, but we need to find out what the z-score is. So we're going to take 4 divided by 3, and we find out the z-score is 1.33. Now we're going to go to what's referred to as the z-table, and that's that big table of numbers that I gave you. So I'm going to show you how you can use the z-table to figure out what our percentile is. When you first look at the z-table, it looks a little bit confusing. But here's how the z-table works. Notice this is labeled with z, so everything on the outside is referring to the z-score itself. The numbers over here are the first digit or the first decimal place of the z-score. These numbers up here are the second digit or the second decimal place of the z-score. So for instance, if I were looking at 0.23 as a z-score, I go to 0.2, and then I go over to 0.03, and where those two things crossed actually gives me my percentile. So the example we're doing right now had a z-score of 1.33. So I'm going to go to my z-table, and I'm going to look for 1.3 first of all. I find it here. Then I'm going to go across to where I have that second digit of 3, so 0.03. And I'm going to see where those two things cross one another. So when those two things cross, I get this, 0.9082. Well, that's the percentile as a decimal. We want it as a percentage. So 0.9082 is really 90.82%. So answering their question, once we found out that z-score was 1.33, the percentage or the percentile now is 90.82%, and that came from the z-table. So if we don't want to benchmark, those take a little bit more work, just because we got to find the z-score and then we got to look it up. All right, so let's do another example where we have to use the z-score from the z-table to help us out. All right, so we're going to look at ACT and SAT, their scores. And we're told that they have a normal distribution. And with the ACT, the normal distribution has a mean of 21 and a standard deviation of 4.7. The SAT has a mean of 1025 and a standard deviation of 210. And then we're going to be asking questions related to that. So here's the first question that we're asked. Ryan takes the ACT and he got an 18. he wants to know what percentile that puts in relation to the other students that took the test. Now, ordinarily, we'd sketch the curve and we'd see if it's on one of the benchmarks. But all these examples I chose because I want to practice with the z-table. None of these will be on the benchmarks. So we're going to go straight to finding the z-score on this one. So let's see what Ryan's z-score would be based on knowing he has an 18. Well, he had an 18. The mean for the ACT was 21. And the standard deviation was 4.7. So this one will have a negative z-score, which is fine. It comes out to be a negative 0.64. Now remember, that's the z-score, not the percentile. So we're going to try to find what his percentile is. Well, that first example we did had a positive z-score. So that's why we use this side. But on the back side are all the negatives. So I'm looking for 0.64, which means the first decimal I'm looking for is negative 0.6. So I'm going to go down here to where negative 0.6 is. Then I'm going to go across to where the 0.4 is. And when I do that, I get this 0.2611. Or in other words, he's at the 26.11 percentile. Or in other words, 26.11% of the values were less than his. A good way to check yourself, anytime I have a negative z-score, would our percentile be more or less than 50? If I have a negative z-score.
Less.
Yeah, it should always be less, right? Because we know the mean is right at 50. So if I had a negative z-score, that means I was less than the mean. So I'm going to be less than 50. If I have a positive z-score, like we did on this last example, I should be bigger than 50. All right, let's see about the percentage of students who took the SAT this time. We want to know what percent scored higher than 950. That part's going to be important here eventually, but we're going to still start with our z-score. So we're going to take the 950, we're going to take away the 1025, because that's the mean, and that's divided by the standard deviation of 210. So I get a negative 0.36. So I'm back to my z-table. I'm on the negative side again. So I'm looking for negative 0.3 first of all. Then I'm looking for the 0.6. And I get 0.3594 or 35.94%. However, I threw in the fact that, or I circled the fact that we wanted higher than 950. Because that 35.94 really tells me the percentage that are less than 950. So how do we find that percentage that's higher than 950? What's the extra step we got to take? Yeah, like we did earlier. So we're going to take this amount, we're going to take it away from 100. So I'm going to be looking at roughly, 64.06%. So if they say higher, greater than, above, something like that, we got to take that extra step, take it away from 100. All right, last example here. This one, they want to know what percent of the students who took the ACT, so we're back to ACT, scored between a 17 and a 22. Well, for a problem like this, we really are going to do two different things. We're going to focus just on the 17, and then we'll focus just on the 22. So when we focus just on the 17, I'm going to do what we have been doing. I'm going to start with the Z-score. So I'm going to take the 17 minus the 21, divide by 4.7. Get negative 0.85. So go to your Z table now and see if you can figure out what the percentage is for negative 0.85. So what's that percentage? Yeah, 19.7. Okay. Now we start over with the other value. So we're going to find the Z-score for the 22 now. Now we're doing 22 minus 21, or 4.7. Positive Z-score, 0.21. So now make sure you go to the positive side. And that should be 58.32. Now the question wanted to know what percent scored between those two values. Well, now that I have the two percentages, I'm just going to subtract them. So in between those two would be whatever I get when I take 58.32 minus the 19.77. So in between those two is roughly 38.55%. So again, really there's only three types of problems you can see. You're going to have the percentage that are less, percentage that are more, and the percentage in between. And the Z table can help you figure that out. All right, so I know a lot of information. That was actually 2 sections worth of information today. The good news is that's pretty much all the new information that you'll have to know for this chapter. So on Wednesday, we'll just do a lot of practicing with these type of problems, looking at slight variations to them, but for the most part, new information. And then Friday at some point, we'll have a quiz over these things. What I'd like to do though for Wednesday is I have just 4 problems related to the z-scores and the normal curves. So this will be an assignment for Wednesday, but I think you can finish it here in class, you should be able to. And I kind of like to be able to see what you come up with, so I have an idea of what we're catching on to. And I noticed on that first one, when you read through there, it does ask you to sketch and label the normal curve, so make sure you do that on the first one.